The last time we were looking at this differential equation. It was somewhere around here. Sorry, 1 second. There we go. It was dx dt equal to -1 times x plus 2 times y. And dy dt was equal to -3 times x plus 4 times y. And we had some initial conditions as well. The initial conditions were that x of 0 was 2, I believe, but let me double check that. Sorry, I've got notes all over the place here, and I'm less organized than I should be. Yeah, x of 0 is equal to 2, and y of 0 was equal to 4. And we found the solution to the system of differential equations of linear differential equations. See? The solution was the vector, which is just the first function x of t, the second function y of t, and it was equal to -2 e to the t times 1 plus 2 e to the 2t times 2 3. That's what we did last time. That's a very brief sum up of what we did, right? We started with this, we did a bunch of work, we found eigenvalues, eigenvectors, all kinds of stuff. And at the end of the day, we found that this was the solution. We even showed it was a solution. A couple of things to observe here. If we look at just the first coordinate, which again, I'll remind you, the x was like the population of wolves and y was the population of deer. So if we look at x of t, just the first row here, it's negative. Oh, this was low. Sorry, 1 second here. Yeah, there we go. That's not too close. Yeah, that's fine. Just so I'm not bending over quite so far to write this. So -2 e to the t times 1 plus 2 e to the 2t times 2. What I want to point out is that as t gets larger, as time goes on, you're going to get negative infinity plus infinity, but this thing here is definitely going to overpower that thing there. If you really wanted to, you could say the limit as t goes to infinity of this. If you weren't convinced that this infinity overpowers that infinity, you could factor out an e to the t. If I factor out an e to the t, I'm left with -2 plus 4 times e to the t. And now as t goes to infinity, that goes to infinity, that certainly goes to infinity, and infinity times infinity is infinity. Or in other words, if we let time go on forever without any sort of other influences on the system of differential equations, the population of deer will grow infinitely large. In a similar way, look at y of t, which is -2 e to the t plus 6 e to the 2t. Well, that will also get infinitely large as time goes on. So that goes to infinity as time goes to infinity as well. That's not super duper helpful on its own, but it does kind of give us an idea of what's happening here. I would say that both of these populations are unstable, right? We have an unstable equilibrium because we're not honing on any one particular value for x and y. Which kind of makes sense if you think about it a little bit, right? If you had deer and wolves, for example, and I'm going to say this is kind of a general statement, for a system of linear differential equations like this, the only stability point, or I should say, sorry, the only equilibrium point is the origin, where both the number of deer and the number of wolves is 0. It's not really a stable equilibrium because if you move away from it just a little bit, the populations grow, right? They don't usually tend back towards 0 when you're talking about animals like this. So it seems reasonable that this equilibrium point would be unstable. But let's actually see it. So, and actually, this is something I wanted to point out to everybody here. If you look at Canvas, and if you look at the modules, which I guess is also on this page here, but whatever, I just clicked on it. If you scroll down just a little bit, you'll see the link to graphing a phase plane from a system of differential equations, which I think is useful. And if you open it, you got this set up here. So Over here, you can write your differential equation dx dt. You make sure that if you use this just to see what things look like, when you multiply things, you do have to include the little asterisk symbol to multiply. Like if you just write like 0.5x, it won't read it correctly. So for this one here, my differential equation was negative x plus 2 times y. That was what dx dt was equal to, and dy dt was equal to negative 3 times x plus 4 times y. You can change your display to have a wider or a narrower field of vision. Let's go negative 10 to 10, just to kind of give us a little bit more space to work with. And then we can graph it. And that's what it looks like. So you can see here that if you are starting anywhere other than at the origin, you're going to get pushed away from the origin. Right? If I start right here, the graph is saying, oh, well, then go in that direction, and then go in that direction, and then go, right? You're moving away from your equilibrium point no matter where you start. And you can actually click on this, and it'll show you the trajectory based on what point you're starting at. It's kind of neat. So this is kind of like saying, here's my solution to my differential equation. And if I start at the point x equal to 2, y equal to 4, which is over here, x is 2, y is 4, about right there. Right? That was the initial condition that we gave ourselves in this problem. It shows you that's your trajectory along that path that has that initial condition, certainly moving away from the origin. This is the tool I like to use because it just kind of shows me stuff. We're not typically being asked to graph these direction fields because, as you can see, it would be terrible to have to graph this by hand. But it's nice to kind of see what things look like when we're talking about whether we want to see if something's stable or unstable or a saddle. So we're going to talk a little more about that today, but this is kind of the idea behind that. We can look at these things. Yeah. So just to kind of sum up here, we would say that this system of differential equations is classified as an unstable source or an unstable node. I think we actually don't, I think we just use the word source. We don't say unstable source. So when you think of it as a source, I'm thinking of everything emanating from the source outward. So unstable. Let's look at another example. Unless there's questions. Oh, sorry, you can't see the thing I just wrote. I'm like, yeah, sorry about that. There we go. This is classified as a source, also known as an unstable node. Come on in. Cool. So let's look at some more examples, because a lot of what this section of this course is taking systems of differential equations and either finding the solution, which is kind of a lot of work, or just classifying to see if it's a sink or a source or a saddle or a spiral. There's lots of options. There's like 6 options. But it's really, once you know how to classify them, classifying is really not that terrible. So let's look at a new example. Oh yeah, let's look at this example. Let's look at example. So let's say we have the following. So here's our system of differential equations that we're going to solve. And I'm going to do, instead of using x and y, I'm going to use x1 and x2 this time. So we have dx1 dt equal to just x1 and dx2 dt equal to 4x2 4x1 minus x2. And we also have initial conditions. We are given that x1 of 0 is equal to 2 and x2 of 0 is equal to 10. For graphing purposes, if you do have to graph something like this, you should definitely think of x1 as x and x2 as y. The first thing is always our x horizontal thing. The second thing is almost always our y vertical thing. So let's write the matrix equation. So that's kind of the first step. So my matrix equation, we're going to rewrite it as the vector of derivatives, dx1 dt, dx2 dt, equal to the coefficient matrix, we'll fill in a second here, times the variables x1, x2. And the variables that go here, or I should say, pardon me, the constants that go here are just the multiples of x1 and x2 in order. So the multiples of x1 and x2 in the first equation are 1 and 0. And in the second equation are 4 and -1. These two things I've written here are the same thing. It's written differently. But really, right, if you multiply this out, this is just saying dx1 dt equals 1 times x1 plus 0 times x2. And dx2 dt equals 4 times x1 minus 1 times x2. Literally the same equation I've written there. But we're writing it as a matrix equation, so then we can find the eigenvalues and do all the stuff we did before. Let's find the eigenvalues. So we're going to solve the determinant a minus lambda I equal to 0. By the way, I asked that last time I was saying I is the identity matrix. I think your teacher might have called it the unit matrix or something. I don't know. It's the matrix with the ones on the diagonal and zeros everywhere else. Or you could think of it as like the number 1. It's the thing that if you multiply by it, it doesn't change it at all. So here we're finding the determinant of our matrix minus lambda in the diagonal spots. 1 minus lambda, 0, 4, -1 minus lambda. We're going to set that equal to 0. And this matrix is kind of special, which we'll point out in a second here. But if we solve this, I'm going to have 1 minus lambda times -1 minus lambda minus 0 times 4 equal to 0. Do not multiply this out. What's 0 times 4? So look, this is already factored for us. I've got 1 minus lambda times -1 minus lambda. There is no good reason to multiply this out and then factor it again to find out what the solutions are. It is already factored for you. So our solutions are going to be, one more time? Oh yeah, exactly, yeah. Lambda 1 equal to 1 and lambda 2 equal to -1. It doesn't matter what order you call things in. I feel like we often say if they're opposite signed, we usually call lambda 1 the positive one. If they're both positive, we usually call lambda 1 the bigger one. But really, whatever you decide to call them is totally fine as long as you make things match. Okay, here is something that is always true. If your matrix looks like this, which is called a lower triangular matrix, where everything above the diagonal is 0. Or if your matrix looked like, just as a side note here, if your matrix was something like 3, 5, 0, 9, which is called an upper triangular matrix because everything below the main diagonal is equal to 0. If your matrix is triangular in either way, or in other words, has a 0 in that spot or in that spot, your eigenvalues will always be just the diagonal elements. So we didn't even really need to do any of this work here. We could have seen from the get-go that the eigenvalues were going to be 1 and -1. In a similar way here, you should all at least verify in your own minds. In fact, we'll just write it over here real quick. The eigenvalues for this matrix here, even though we don't really care about it, are +3 and +9 because of the way we solve it. If you're going to try and solve, sorry, and I'm taking up all my room over here. If I was going to try and solve the determinant of that matrix minus lambda I equal to 0, you're just going to end up with 3 minus lambda times 9 minus lambda minus 0 equal to 0. So it's already factored for you, and the factors tell you that the eigenvalues are exactly the diagonal things. So the reason I mentioned this is because a lot of the time, especially on exams, your teacher is going to try and help you out kind of by giving you a matrix that's either has a 0 in the upper right-hand corner or in the lower left-hand corner. And you can just easily read the eigenvalues without having to do any of the work. It's kind of nice. All right. What I want you to know about this is that when your eigenvalues are opposite valued, like in this case here, it's going to mean we have a saddle. And in the previous example, when your eigenvalues were they're both positive, I believe. Yeah, they're both positive. It's going to mean that you have an unstable node. Oh, there's a question or a comment. Let's see what it is. Can you move? Oh, yes. Sorry. I know. I zoomed in a little, or I didn't zoom in, but I like moved my table up. So it's a little, yeah, there you go. Hope that's a little better. Like a yes, it is. Yeah, of course. Yeah. All right. In fact, I can do this too as well. That probably helps a little tiny bit. All right. So, I will do that. We'll do yeah. There's a thing I wanted to show you as well. So these being opposite value or opposite sign, they don't have to be the same. Like it could be like 2 and -3 or 5 and -7 or any two numbers where one's positive, one's negative. That means we're going to have our equilibrium is a set. We're still going to find the solutions though, because that's really kind of the meat of most of these questions is we want to solve it. So after we find the eigenvalues, what do we find next? The eigenvectors. Again, I will point out there are two ways to find the eigenvectors, and they both have their merits. I will show you both ways again because I think they're both valuable. So to find the eigenvectors, we have to start with each eigenvalue. So for lambda1 equal to 1, we want to solve A times the eigenvector equal to lambda times the eigenvector, which in this example is going to be solving 1, 0, 4, -1 times the unknown eigenvector equal to lambda, which is 1 times the unknown eigenvector. This is my preferred way of doing it. And I would say this is the better way of doing it unless your eigenvalues are gross. So if your eigenvalues are really like kind of not nice integers, if they have like irrational pieces to them, then actually doing it the other way, which we'll mention here in a second, is probably easier to do the algebra for. So let's see, multiplying out the top row, I get 1 times x1 equal to 1 times x1, which is not particularly helpful. That doesn't really tell me anything. X1 could be anything. X2 could be anything. There's no conditions here. So when that happens, and that will happen when you have something that's upper or lower triangular like this, move on to the second equation. So instead of dealing with the first row, deal with the second row. The second row says 4 times x1 minus x2 is equal to x2. That's much more helpful. Yeah. So I get 4 times x1 equal to 2 times x2. I would divide both sides by 2 and say 2x1 equals x2. And then we usually just say let x2 equal 1. So if x2 equals 1, then that's probably not the choice I would actually make here. Sorry. We could do it that way, though. You could say x2 is 1, and then x1 would be 1/2. I don't love that choice, though, because then my eigenvector has a fraction in it. So instead of saying that the first eigenvector is 1/2, 1, which is a fine, totally reasonable choice, I would rather multiply that by some integer to make everything non-fractional. So instead, let's multiply that by 2 and say our eigenvector is actually going to be 1, 2. That is the more standard choice. Technically, you could make any choice that's a multiple of this. You could pick 2, 4, or 3, 6, or 5, 10, or anything where the second component is twice the first component. Except for what vector can't I pick? 0, 0. I'm never allowed to pick 0, 0 as the eigenvector. Anything else will do as long as it's a multiple, except for 0, 0. Cool. So there's our first eigenvector. And then to find our second eigenvector, we do the same kind of thing. So for lambda 2 equal to -1, you could do it this way. I would encourage you to do it this way. This is my preference. fact, I'm gonna do it that way, and then I'll show you the other way because it's just I think it's better. So I'm gonna do now my matrix 1, 0, 4, -1 times x1, x2 equal to -1 times x1, x2. And now looking at the first row, I get 1 times x1 equal to -1 times x1. Which means x1 has to be what? If x1 equals -x1, there's only one number that's its own negative. 0. -0 is still 0. The easier way to do this is to add x1 to both sides and say, oh, I've got 2 times x1 equal to 0. So x1 equals 0 divided by 2, which is 0. Okay, so I found one component of my eigenvector. One of the components, the first component is 0. What is the only thing the other component can't be? Also 0. Can't pick 0 for, right? I can't have 0, 0 as my eigenvector. But if one piece is 0, then the other piece is whatever you want. I'm going to pick 1. Most people are going to pick 1. But technically, you could say 0, 1 or 0, 2 or 0, 7 because all of these are multiples of each other. But we're going to pick this one because it's the one that has the smallest possible integer choice. So you should just expect that when someone is asking for an eigenvector, the way they're typically going to write it, if they can, is as an eigenvector that has integers as the values that are as small as possible. So no one's going to pick 3, 6 when they can pick 1, 2. No one's going to pick 0, 5 when they can pick 0, 1. They're always going to try and pick the smallest possible integers, preferably positive. But sometimes you have a positive and a negative. I couldn't see the bottom of the last page. Okay. There's the last page. Sorry, but now we can't see the bottom of this page. That should be, there we go. There's all the pages all at once. The reason I like talking about eigenvectors in this way is because it really, to me, makes sense. An eigenvector is literally a vector that if you multiply the matrix by the eigenvector, you just get another vector that's pointing in the same direction. That's what's special about an eigenvector, is multiplying by the matrix. It might lengthen it or shorten it or actually point it in the opposite direction, but it's still going to be pointing along the same line that the original vector was in, which is kind of special when we start talking about the eigenlines and the null lines. So let's go ahead and just briefly here mention how, although we could do it this way, where we solve, again, a times b equal to lambda times v. If you prefer, it is always an option to solve a minus lambda I times your eigenvector equal to 0. That is also a choice. If we were doing it that way, we'd be solving 1, 0, 4, -1 minus -1 times the identity matrix times the vector that we're trying to find equal to the 0 vector. Simplifying this equation on the left-hand side just becomes, let's see, 1 plus 1 is 2, 0 plus 0 is 0, 4 plus 1 times 0 is 4, and -1 plus 1 times 1 is 0. And then either equation is going to either give you 2 times x1 equals 0 or 4 times x1 equals 0. So either way you slice it, you're ending up getting x1 equal to 0. Same as the first way we did it. Right? The first way we did it, we also got x1 equal to 0. And I just want to remind you, because this happens pretty often, if you're finding the eigenvector and one of the two components is equal to 0, you automatically get to pick the other components to be whatever non-zero number you like, and the standard choice is +1. All right, we have all the pieces we need to write the general solution. And also the particular solution once we fill in the initial conditions. So let me remind everybody, or let me show you all again. Remind is kind of a cruel word. It's like, let me remind you something you're supposed to know. Here's something you're eventually supposed to know by heart. Our solution is the vector x of t equal to x1 of t in the first component, x2 of t in the second component. And it's just going to be c1 e to the lambda 1 times t times v1 plus the same thing with 2's instead of 1's. c2 e to the lambda 2 t times v2. That is the general format of the solution to this system of linear differential equations. And then we're just going to plug in all the things we know. We know lambda 1 and v1. We know lambda 2 and v2. So writing my solution. Also, just as in general, if you have questions, you should ask them, right? I'm happy to stop, back up, clarify. Just say something if you want. Yeah. Maddie, do you have a question?
Wait, so when you do the matrix for V2?
Yeah, the eigenvector for V2.
So why did you get to choose?
So what I'm saying is I could have done it this way over here too. It doesn't matter which vector. I'm just saying if you're trying to solve this equation, let me back up here. Pardon me, sorry, 1 second. So if you're trying to solve this, it's equivalent to solving, or is the same as solving a minus lambda I times your vector equal to the 0 vector. So what I'm saying there is you can pick whichever way you want to do it.
Yeah, but for the V2, why is it like 1 or 2 or 7?
Well, just for the same reason that for the V1, it's 1, 2, or 3, 6, or 5, 10. Because any multiple of your vector is also an eigenvector. It just feels a little bit like it feels weirder here because of the 0, but technically, right, 0, 2 is a multiple of 0, 1. 0, 7 is a multiple of 0, 1. They all point, all those vectors point straight up, right? Either 1 up or 2 up or 7 up. They're all pointing in the same direction. And eigenvectors for a particular eigenvalue always point in the same direction. All of these eigenvectors also point in the same direction, over 1 and up 2, or over 3 and up 6, or over 5 and up 10, right? They're all pointing in the direction of the line y equals 2x. These are all pointing in the direction of the line x equals 0, straight up. Which is why we will start eventually talking about the eigenline, because the eigenline is the line that all of your eigenvectors will lay in if they emanate from the origin.
Understand that the V1 value is 1, 2, so the 2 over 1 is a slope.
Correct. But really, it's easier to see it just from here, right? If you use, and this is why I like to use y as an x instead of x1 and x2. If you think of this as just 2x equal to y, it's literally just the line y equals 2x, which has a slope of 2. But yeah, if you have a vector, the slope is always just the second coordinate divided by the first coordinate, unless it's this vector, right? Because then the slope is undefined, which is a vertical line, which it should be. Good questions. So then, back over here, writing our solution, our general solution is going to be c1 e to the lambda 1 was 1 times t. v1 was 1, 2, plus c2 times e to the lambda 2 was negative 1 times t, times v2 was 0, 1. There is our general solution. Let's go ahead and find C1 and C2, because if we were given initial conditions, right, we were given x of 0 was equal to, I forgot, I think it was 10. No, 2, and y of 0 was equal to 10. Oh, except x2, not, sorry, x1 and x2, not x and y. So all we're gonna do with this is we're gonna plug in t equal to 0 and x1 of 0 equal to 2 and x2 of 0 equal to 10. So right here is where I'm plugging in the 2 and the 10. So I have 2, 10 equal to C1. Okay, this is going to happen enough times. We don't want to write it every time. What's e to the 0? 1. Every time you plug in t equals 0, the e to the whatever part's just going to go away. So e to the 0 is 1, e to the 0 is 1. Let's not write it. This one is really easy to solve because we have a 0 somewhere. If you look at the first row says 2 equals C1 plus C2 times 0. So C1 is equal to 2. The second row says 10 equals 2C1 plus C2, but we know C1 is 2, so we've got 10 equals 4 plus C2, so C2 is equal to 6. There are lots of ways to solve this, so yeah, do I really want to talk about that? She's not there yet. Sorry, there's another way of solving this that sometimes becomes useful. I don't know how much she's going to talk about it though, but let me just point out. You could do this a different way. You could write this as a matrix equation. You could say 210 is equal to the matrix 1, 0, 2, 1 times the vector C1, C2. And then you could solve this by multiplying both sides by the inverse matrix. In 17b, someone was supposed to have taught you how to find the inverse of a 2x2 matrix. They might have, they might not have. It's kind of not that big a deal. But if someone wanted you to solve this way, you could find the inverse of this matrix, or the inverse of a matrix, of a 2x2 matrix in general, is equal to 1 over the determinant of that matrix. And then what you do is you switch the diagonals and you change the signs of the off diagonals, which is a little annoying. But it's actually really easy to do for a 2x2 matrix here. So check this out. If our matrix here is the matrix 1, 0, 2, 1, then the inverse matrix is equal to, let's see, so the determinant of this matrix is 1 minus 0. Well, that's easy enough. That's just 1. And then I'm switching the off diagonals, which are 1 and 1. Or sorry, the diagonals, apologies. I'm switching the diagonals. 1 and 1 switch and become 1 and 1. And the off diagonals, I change the signs. Negative 0 is still 0. Negative 2. What does it mean to say that something, what does it mean when I talk about the inverse of a matrix? Well, when you multiply two inverse numbers together, like 3 and 1/3, what do you get when you multiply 3 times 1/3? You get 1. When you multiply two inverse matrices together, you get the identity matrix. So this matrix times that matrix would give you the identity. I'm like, I think. Yeah, 1, 1. Yep, totally. It should. So the point is, you can multiply both sides of this equation by this matrix. So check this out. And you might not want to write this down right now, but if I multiply both sides by this, oops, that's a 1. And over here, when you multiply this matrix by this matrix, well, 1 times 1 plus 0 times 2 is 1. And 1 times 0 plus 0 times 1 is 0. And negative 2 times 1 plus 1 times 2 is 0. And negative 2 times 0 plus 1 times 1 is 1. Oh yeah, we get the identity matrix there. And what's special about the identity matrix is that when you multiply the identity matrix by any other matrix, you just get that other matrix. It's literally like multiplying by 1. And you do, right? This times that, 1 times C1 plus 0 times C2 is C1. 0 times C1 plus 1 times C2 is C2. On the left-hand side, 1 times 2 plus 0 times 10 is 2. Negative 2 times 2 plus 1 times 10 is negative 4 plus 10, which is 6. Oh, look. We get the same values for C1 and C2 as we did doing it this much easier way over here. I don't think you should do it this way, but your teacher might want you to do it this way. She might think and sometimes it's less terrible to do. Like sometimes it's really easy to solve it just straightforwardly. Sometimes doing this work is actually a lot harder, especially when the numbers are a little bit messy. So this is another way of solving for the constant C1 and C2. So here's what we've got. We have got our final solution here. Now, if I can move the papers around, we have that x of t, which is just x1 of t, x2 of t, equal to c1, which we found to be 2, times e to the t times 1, 2, plus c2, which we found to be 6, times e to the negative t times 0, 1. Typically in web work, they won't ask you to write, they won't ask you to write this out like this. They will actually ask you for each of the top part and the bottom part separately. So separately, we could say that x1 of t is 2e to the t, and that's it. Right? There is no other part here because it's that times 0. And x2 of t is 2 times 2 is 4e to the t plus 6e to the negative t. That is what our solutions look like. Long term, what's happening here? Well, again, both things are getting infinitely large. As t gets bigger, as time goes on and on, 2e to the t is going to go to infinity, and 4e to the t is going to go to infinity, and 6e to the negative t is going to go to 0. But overall, that's still going to go to infinity. So long term, x1 of t goes to infinity as time goes on and on and on, and so does x2 of t. Not very exciting so far. I would love to see some equilibrium here, but we're not there yet. We're almost there though. Yeah, guess we can do that. Sure. So let's. So the problem here is like I feel like we're like she's not quite talking about the stuff in class just yet. She's about to though. I'm just not sure which way she's going to go. Like because some people do things a lot more graphically than others. So here's something we sometimes do with this. No, we'll come back to the graphing if we need to, because I want to kind of show you some other stuff here. So let's go that way. Sorry, 1 second. Yeah, let's do that. Cool. So I will point out though that this equilibrium, what is the equilibrium? Let's go back and look at our differential equations. We had dx1 dt equal to x1 and dx2 dt equal to 4. Nope, not 4. Sorry, I lost my spot here. Let me just look over here. Wow. Thanks. 4x1 minus x2. Yeah. It should have been 4x1. I think I accidentally wrote x2 and then scratched over with an x1 there. I know it was terrible. For a linear system of differential equations, for a homogeneous linear system of differential equations where you don't have any other constants added on or subtracted off, the equilibrium is always 0, 0. Because that is the only value of x1 and x2, or x and y, that'll make both of these derivatives equal to 0. And as a reminder, right, just thinking kind of bigger picture, an equilibrium is a place where things aren't changing. And if things aren't changing, the derivative has to be 0. And the only way for both of these to equal 0, well, x1 has to be 0, and then if x1 is 0, x2 also has to be 0. And it's always going to be the case because you're just going to have two lines, and where they cross is going to be the origin because they both have the origin as their intercept. So this equilibrium is a saddle. Okay, I said I wasn't. I can't not draw things here. Here's what I want you to see. I'm going to draw the eigenlines, which we already know are the lines y equals 2x. Don't draw arrows at the end of your lines. I know it's hard not to, but trust me, you don't want to yet. We're going to in a second. And then the other eigenline was x equal to 0. For the positive eigenvalue, which was lambda equal to 1 associated with the first eigenline. So this lambda 1 equal to, it was 1, right? Yeah, it was 1 and negative. Yeah, it was 1 negative 1. If the eigenvalue is positive, it means you're pointing away from the origin. Another way to say that is if I start on this point here and multiply by the matrix, I'm just going to point in that same direction again, because the matrix times the eigenvector is going to give me 1 times the eigenvector, or whatever the eigenvalue is times the eigenvector. On the other hand, this other eigenline here is associated with an eigenvalue that has a negative eigenvalue. Lambda 2 equal to negative 1, which means if I start, say, like, for example, if my initial vector was 0, 3, and I multiplied the matrix by it, my return would be 0, negative 3. In fact, let me show you. Take 1, 0, 4, negative 1, and multiply it by a vector that's on this eigenline. Check it out. I get 1 times 0 plus 0 times 3, 4 times 0 plus negative 1 times 3. I get a vector pointing in the opposite direction it was. So whatever direction I go in, the eigenline is going to point me back in the opposite direction towards the origin. So if your eigenvalue is negative, you're going to get pointed back towards the origin. And so here's how this kind of works. If you start at a point that's on either eigenline, you just get pointed in the direction of the eigenline. Because on the eigenline, the matrix just multiplies by it and gives you a multiple of that value. But if you start off of the eigenline, like if my critical point, if my initial point was like over here, well, then I'm in a section where I'm going up and that way. So I'm going to kind of get pushed that way. If I started something like right here, I would get pushed kind of up and then back like that. So basically the two kind of eigenlines in between tell you which way you have to go. There's more to it than that, especially when we start talking about the nullclines, also called the zero isoclines. But for now, this is kind of a nice way of seeing it. So whichever kind of quarter we start in, you're going to get pushed that way, or that way, that way. So we have something that very much looks like a saddle, right? You're kind of going away from the thing in one direction and towards the thing in the other direction. Which is why it's called a saddle. Anything else I really want to say about that? No, not a whole lot. Oh, yeah, one more thing. Sorry. One more. Well, yeah. Not at all. Sorry, I know. It's hard to stay in focus here. There is one more thing I want to say about this example, and then we'll look at another example and also talk about kind of another way of finding the eigenvalues.
Okay, this graph is this similar to slope field?
Yes. So what we're doing, so in fact, let me actually show you. How do you determine the two red lines? So those are the lines that come from the eigenvectors, or the eigenlines. So if I go back to when I was finding the eigenvectors, and it was a while ago, the first eigenvector, my eigenline, was the line x2 equals 2x1, or y equals 2x. So literally the line y equals 2x. And my second eigenline came from setting x1 equal to 0, or just x equal to 0, which is the vertical line along the y-axis. So you can also, you can either actually find the equation of the line, or you can say, I'm going to draw the vector over 1 up 2, and then draw the line that goes from the origin through that point. Over 0 up 1, draw the line from the origin through that point. there's one more thing to say about this, which is kind of what the behavior of X and X1 and X2 look like. So we had X1 of T equal to, why do I not remember anything here? Equal to 2e to the T. So we graph that. So there's a couple different kinds of graphs going on here, right? The one we were just kind of talking about is like the phase plane or the phase plot, whatever you want to call it. Whereas here, where you're graphing X and Y, and then you're kind of looking at different values of T. Whereas here, we're actually plotting X1 versus T. And we're just seeing, oh, well, as time gets bigger and bigger and bigger, X1 is going to get bigger and bigger and bigger. Similarly, X2 of T equal to, I forgot what it was, 4e to the T plus 6e to the negative T. If you plug in T equals 0, you start off with a value of 10. And I think there's a little bit of a dip before it starts getting bigger and bigger and bigger, but essentially it does something kind of like this. Which kind of makes sense if you think about back to our other graph. If you think about starting at the point 2, 10, which is like way up here. Oops, you can't really see that here. Which would be like way up here. You probably have like a little dip first before you turned around because you're not quite on the eigen line to start with. But yeah, just to kind of answer the question you actually asked before, which was, are we drawing the phase plot? Yeah, we're kind of drawing a bare bones phase plot. Like we're trying to get all the information without having to draw like a bajillion little points. So you could go back to, and I really recommend for all of you playing around with the phase plane plotter. I think it is worth your time to look at this, at least to just once or twice to see what a solution might look like. If we go back and we plug in our original differential equation, which was X, and then it was 4 times X minus Y. Right, does that seem right? I think it is. It's always good to be sure before you start. Yeah, cool. If we, let's go back. I think the -5 to 5 actually might look better. Graph that. So you can kind of like, and so then if I go over and like plot some initial points, oh yeah, look, it's just going away, away, away. And if I'm up here between X equals 0 and Y equals 2X, I have that kind of behavior there. And if you plot a bunch of points, you can kind of see, oh yeah, you've got this saddly looking behavior. Kind of neat. It's really, I think it's really fun to play around with this. I'm not gonna lie. It's kind of interesting. Was there a question? Okay, cool. So let's do another example, and we're gonna talk about another kind of aspect of this. Where, oh yeah, sorry, it's in my phone here. Let's grab that. So let's look at this example. We have dx dt equal to -2x plus y, and dy dt equal to 2x minus 3y. And there are other ways of finding the eigenvalues other than just doing the determinant of a minus lambda I equal to 0. In fact, let me show you very generally here because I think it's worth your while. So if my matrix was just some general matrix A, B, C, D, and I want to find the determinant of A minus lambda I equal to 0. Well, that's the same as saying the determinant of A minus lambda, B, C, D minus lambda equal to 0. We multiply this out, we get A minus lambda times D minus lambda minus B times C equal to 0. Multiplying that out, negative lambda times negative lambda is lambda squared. I get negative lambda times D plus negative lambda times A, and I'm going to write that as negative A minus D, sorry, times lambda And then I get A times D minus B times C. But these two things are actually kind of special. I'm going to rewrite this just slightly. This is lambda squared minus A plus D times lambda plus AD minus BC times 0. AD minus BC, if you look at the original matrix, A times D minus B times C is the determinant of the original matrix. And A plus D is called the trace of the matrix. And so if you wanted to, instead of doing all this, finding a quadratic equation, trying to factor it by set, or trying to set equal 0 and factor it, you could say, well, I know I'm always going to get lambda squared plus negative trace plus the determinant, and then I could just use the quadratic formula and say that my solutions are going to be negative b, which is the negative trace, so it's the trace. We use the symbol tau for the trace. We use the symbol capital delta for the determinant, minus the square root of b squared. So the negative trace squared is just the same as the positive trace squared, minus 4 times 1 times our c value, which is delta, all over 2. That is another way of finding the eigenvalues. It's sometimes nice. It's more really nice if you don't really care what the values are, if you're just trying to tell if they're both positive or both negative or one of each. Something I think that is worth observing here. If your determinant's negative, then minus 4 times a negative number is positive, and tau squared plus something, if you take the square root, let me ask you all. So everybody, real quick, what's the square root of 5 squared? 5, right? Square root of 5. Now, if you take 5 squared and you add something to it, and then you take the square root of that, the answer is going to be bigger than 5. And so the point is, whatever this is here, if delta is positive, this thing, oh, I forgot a plus or minus there. I was forgetting something. If delta is negative, then this whole thing is going to be bigger than whatever that is. So when you add this and subtract it, you're going to always get one positive thing and one negative thing. So it's just interesting to note that if the determinant of A is negative, then lambda 1 and lambda 2 will always have opposite signs, which means we'll have a saddle. All right, so let's do this one both ways, just to kind of see how it works. So we could say that if our differential equation, our matrix differential equation, dx dt dy dt, equal to our coefficient matrix, which is -2, 1, 2, -3 times xy. All right, so just so everybody knows here, if I call this matrix A, the trace is equal to -2 plus -3, which is -5. The determinant is equal to -2 times -3 minus 1 times 2, which is 6 minus 2, which is 4. And then my eigenvalues are going to equal the trace plus or minus the square root of the trace squared minus 4 times the determinant, all over 2, which is going to equal -5 plus or minus 25 minus 16 is 9, square root of 9 is 3, all over 2. So my eigenvalues are -5 plus 3 over 2, which is -2 over 2, which is -1, and -5 minus 3 over 2, which is -4. Here's another cool fact. And this fact might actually be cooler. Also note, if you multiply the eigenvalues together, what's -1 times -4? I know it's not an exciting question. It's +4. But importantly, the eigenvalues multiplied together equal the determinant. -1 times -4 is 4. And also, interestingly, the eigenvalues added together equal the trace. So actually, this I think makes it a little bit more obvious. If your determinant is negative and lambda1 times lambda2 have to equal your determinant, then one of them has to be positive, one of them has to be negative. There is no other choice. It's kind of cool. The reason I'm mentioning all this is because eventually we're going to talk about how we're just going to determine the the stability of your equilibrium based on what the eigenvalues are doing. So in the future, we'll be like, oh, both the eigenvalues are positive. That means we have an unstable node. Both the eigenvalues are negative, as we're going to see here. That means we have a stable node. Both the eigenvalues, or the eigenvalues being opposite signs, means we're going to have a saddle. So that's why we're talking about this, because doing this is sometimes easier than doing all of the work of actually finding the actual eigenvalues. All right, we've got the eigenvalues. Let's find the solution. It's good practice to find the solution. I know it's kind of a lot, but it's really not that bad. So lambda1 equals -1. I'm going to do it the way I think is better, which is we've got -2 times 1 and 2 -3 times my eigenvector equal to -1 times my eigenvector. All right, you can use either row you want. With rare exception, either one will give you something, except for like when you got a 0 somewhere, then sometimes the first equation doesn't help you and you have to use the second equation. But usually the first equation is enough. -2 times x plus 1 times y equals -x. Add 2x to both sides, you get y equal to x. So your eigenvector is going to be 1, 1. Or any multiple that you like, but we're going to pick 1, 1. Similarly, for lambda2 equal to -4, we're going to have -2, 1 to -3 times xy equal to -4 times xy. So -2 times x is -2x plus y equals -4x. So then y is going to equal -4 plus 2 is -2x. So here, my eigenvector is going to be, when I get to this equation here, I just think I'm going to pick whichever thing has the coefficient, set that thing equal to 1. So I'm going to let x equal 1, and then y is going to be -2 times 1. So my eigenvector there is 1, -2. Or -1, +2 would also be a perfectly acceptable answer. I mean, really, again, anything that's a multiple is acceptable, but these are the typical choices. Got eigenvalues, got eigenvectors. Let's actually graph this thing before we find the solution. So if I graph my eigenlines, so I'm going to graph in red. So here's one eigenline, y equals 2x. Again, I know it's really hard for me not to. Don't draw any arrows on your eigenlines until you know which way they're going. And then y equals -2x will be like that. I should use my ruler. I have a ruler. Why am I not using my ruler? Good question. And then I definitely recommend on each eigenline writing the eigenvalue it goes with. Lambda1 equals -1. Lambda2 equals -4. Both eigenvalues being negative means you're going to point back towards the origin. So it looks like no matter where I start, I'm going to end up getting pushed towards the origin. Right? If I were to start over here, right, I probably get pushed somehow like that. What I kind of think about the eigenlines is that they're kind of asymptotes. You can't cross an eigenline when you're drawing this graph. because once you get on the eigenline, the eigenline pushes you exactly in its direction and doesn't veer off of it at all. So eigenlines are kind of like asymptotes in the way we draw them, or the way we draw graphs around them. So like I'm starting right here, I'm probably getting pushed in that way. There can be more curviness. In fact, let's go ahead and look at what this actually looks like, because I think it's worthwhile. Sorry, I know there's lots of things going on here. So let's go ahead and look at instead negative 2x plus y. And 2x minus 3y. Graph it. I feel like these arrows look a lot bigger than they usually do. Maybe it's in my line. Let me change my line width here. Does that not change anything? I guess not. Okay, well, fine. But you can kind of, oh, did I graph the right thing? Oh, no, I didn't. No. Oh, yeah, I didn't. That should be a minus 3 times y, not a plus 3 times y. So here's how I knew I didn't graph the right thing. Looking at this, that looks a lot more like a saddle, where things are kind of going in and then away, or in and then away. And not everything's like just going inwards, which was what I was expecting from what I drew. If I change that to plus 3y, to minus 3y, and now I graph it, cool. Now things are looking a lot more like everything is, no matter where I start, it's going to be pointing inward towards the equilibrium point. So this would be a stable equilibrium, because no matter where we start, we're going to end up getting closer and closer to 0. And we'll see that with our solution in a minute here. Could you explain again how you know which direction the arrow is pointing? Yeah. So the way I know really is by I'm using the eigenlines as guides. And it becomes a little easier once we start talking about the zero isoclines, also called the null clines, because they also give us more guidance. But basically, from here, I can't go this way because I'm kind of directed by these two arrows inward. So whatever two pieces you're in between, you kind of have to look at those and see which way they point you. Now, I'm kind of guesstimating here. It might have been more that I was really kind of supposed to start out kind of going right and then back inward. And again, once we have the other piece of this, it'll make it a little bit easier to figure out what's going on. But for now, I'm just kind of saying, yeah, I know both these are going to point me in. Whereas in the previous examples, right, for the one where we had like a saddle here, this one was pointing me out and this one was pointing me in. So when I started here, I got pointed in first, but then eventually I had to turn back around and get pointed outward that way. I will point out, in a saddle like this, we typically say that the saddle is unstable, but there is one line of stability. If you happen to start off with an initial condition that was on the eigenline with the negative eigenvalue, that would just shoot you straight towards the origin and you wouldn't get pushed off in either direction. So typically saddles are considered unstable, but there is one direction of stability if someone asks. Let's go ahead and finish solving this one, because I do want you to see kind of that we really do get stability. So yeah, and we'll just do a general solution here. We won't, yeah. We'll just do a general solution. Sorry, but keep losing stuff here. Did I give myself an initial condition? I did not. That's totally fine. We don't care. Cool. So we've got our eigenvectors, we've got our eigenvalues. Solution is really not hard to write when you have those things. So our general solution here, again, I think it's really worth writing just the very big format is going to be the vector x equal to c1e to the lambda 1t times v1 plus c2e to the lambda 2t times v2. If you say it or write it enough times, you will just memorize it. You kind of don't have a choice. So here, our solution vector xy, which is what we're calling x of t as a vector, is, we don't know what c1 is, so it's c1e to the lambda 1, which is -1 times t, times v1, which is 1, 1, plus c2e to the -4t times 1, -2. But let's look at the behavior of x and y as time goes on and on and on and on and on. So the first coordinate, x, is equal to 1 times c1 e to the negative t plus 1 times c2 e to the negative 4t. And as time goes on, the limit as t goes to infinity of x of t is the limit as t goes to infinity of c1 e to the negative t plus c2 e to the negative 4t. But as time gets larger and larger and larger, e to the negative t gets closer and closer and closer to 0. And so does e to the negative 4t, right? The graph of e to the negative t looks like e to the t, except it's flipped. So as t gets larger and larger and larger, the values get smaller and smaller and smaller and smaller. So this is going to be 0 because e to the negative t gets closer and closer to 0, and e to the negative 4t gets closer and closer to 0. If you don't like me saying it that way, you could imagine c1 times e to the negative t is the same as c1 divided by e to the t. And then, oh yeah, if t is getting large, e to the t is also really large, and c1 divided by a really large number is really, 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 really small. And in a similar sense, for y of t equal to c1 e to the negative t minus 2 times c2 e to the negative 4t, also the limit's going to be 0 because as t gets really big, both of these t's have a negative coefficient, which means e to the negative large number is going to get super duper small. So this really shows you that no matter where you start at, if you let time go on long enough, your values are going to get closer and closer and closer to 0. So x is getting closer to 0, y is getting closer to 0. So no matter where we start in our phase plane, you're going to get pushed back towards the origin. X equal to 0, y equal to 0. So we have a stable node, also known as a sink. Right? Because the sink, everything drains to the middle part. That's why it's called the sink. So here's the result so far. And I want you to, here's what I want you to know. So as far as classifying equilibria, here's what we've got so far. If both eigenvalues are positive, then the equilibria, which is, then equilibria is an unstable node, also called a source. If both are negative, then the equilibrium, I guess it's singular, not plural, sorry. Equilibrium is a stable node, just like we just saw. Or a sink is another name for it. And then finally, if they're opposite signs, so if lambda1 is positive, lambda2 is negative, or vice versa, but you can just call them whichever way makes sense, then we have a saddle. Which we typically classify as unstable. And if lambda is one of them is equal to 0, it's kind of a pain. We can talk about that next time because it's kind of weird. The other thing that could happen is that your eigenvalues could be imaginary or complex. And that's a whole other bag of things that we have to look at. Not today. Let's see what else we can say about this today. Sure. Yeah, we should talk about, let's go ahead and talk about this other thing here. So let's say, let's go ahead and there is one more, we might as well, we have a few minutes left. For this graph that we just graphed, actually, let's go back to Mahmoud's question and kind of address how I knew how to graph the thing the right way. So in addition to the eigenlines, and I'm just going to graph it again. Ooh, I should use my graph. I have graph paper somewhere. It'd be super useful. Sorry, is there something, did I go too fast? Yeah, totally. Yeah, sorry. This is definitely something you want to memorize for sure. If they're both positive, unstable node, both negative, stable node, one of each sign, settle. Let's go back to not you. Cool. So I'm just going to go back to the beginning thing here and talk about a couple things. So for this system of differential equations, where we had dx dt equal to negative 2x plus y, and dy dt equal to 2x minus 3y. Our eigenvalues were -1 and -4. Not that they're associated with anything particular, just writing them that way. And the eigenvector here was 1, 1. And the eigenvector here was, I don't remember, 1, -2, I think. Yeah, 1, -2. And so the eigenlines, which I'll draw in red, the eigenlines are just the lines that go through these vectors. So the line y equals x, the line y equals, right, -2x, yeah. But there's also something called the null clines. So the null clines, also called the zero isoclines, are the lines where one of your derivatives is always equal to 0. So these are lines where either dx dt is equal to 0 or dy dt is always equal to 0. And they're actually really easy to find, because we already know that dx dt here is equal to y is equal to -2x plus y. So if I want to find what we typically call the x null cline, because we're setting dx dt equal to 0, well, dx dt is equal to -2x plus y. And if I set that equal to 0, it's really, really easy to find the equation of the line. I'm just going to get y equal to 2x. That is one of my 0 isoclines. Specifically, it's the x isocline. So what that means is, on that line, all the arrows can't point left or right, because the change in x is 0. So there's no leftward movement, there's no rightward movement, there's only up and down movement. So on the x null cline, you only get up and down arrows. And similarly, on the y null cline, which we get by setting dy dt equal to 0. Well, if I solve for y to make it easier to graph, I've got 3y equal to 2x, or y equal to 2/3 x. Along that line, all my arrows have to be pointing fully left or fully right, because there is no change in y if dy dt is equal to 0. Cool. So let's try and graph this. And I'm going to graph the x null cline. We're going to graph that one in blue. We're going to graph the y null cline in green. All right. Let's graph the whole thing. How do you graph it? Graphics were really excellent at this moment right now. Of course, no, left it all someone else. That's all right. Let's see. So I want my eigenlines. Oh, I do have a ruler though. Ruler's good. Oh, no, you're fine. It's fine. I'm good. I'm good. So I'm drawing my y null clines. I'm going to draw my eigenlines. So here's the eigenline for lambda equal to -1, pointing inwards. And again, it doesn't have to be exactly perfect to draw when you draw this. It's just, you kind of want your lines to be separate from each other if they can be. And we also have y equal to -2x. So 1 up kind of 2, maybe right about there. The nice thing about all the things we're drawing at this stage is they're all going through the origin, which is great. And then we're going to graph our x null line in blue. That's line y equals 2x. About right there, sure. Don't draw any arrows along your null line yet. Sorry, and then since this is our dx dt equal to 0, so everything is going to be up and down. And then my y null line is y equal to 2/3 x, or really I can think about if x is 3, y is 2. About right there. Again, it doesn't have to be perfect. So this is the let's make that one. Along this line, dy dt is equal to 0. So everything here is horizontal. Everything here is vertical. All right, so now here's something that took me a long time to learn. You get to learn from my experience and mistakes. When you cross a null line, you can only cross it either purely vertically or purely horizontally. Because everything on the null line has to be purely vertical along this blue one or purely horizontal along this green one. So for example, if I was starting right here, I would maybe get pushed this way. Watch for a second. And I'm going to cross this null line completely vertically and then get pushed back that way. So that the tangent line right there to my actual path is a totally vertical line. Often when we draw this, we draw all these arrows on our null line. So all my arrows are pointing down this way. All my arrows are pointing up this way. In a similar way, all my arrows here are pointing to the left. Over here, all of them pointing to the right. So if, for example, I start right here, I'm going to cross this null line horizontally, and then I can't cross as an eigenline. So we can't cross the red lines. We almost always kind of cross the green lines or the blue lines. So that's kind of helping me. I know it seems a little bizarre at first, but once you practice it a few times, it really does become not too terrible. Sorry, how do you know when it points inwards or out? So the inwards or outwards is based purely on the eigenvalues. So if the eigenvalues, like in this case, are both negative, the eigenlines point inwards. If the eigenvalue is negative, that eigenline points inwards. If the eigenvalue is positive, that eigenline points outwards. And I would love to say more, but I should stop because it's 1:31.